Our webinar will be on getting started on Intel oneAPI Base Toolkit. I'll be introducing our speakers for today. It will be Sandeep, Director of NetWeb, and Subina, Technical Consulting Engineer from Intel. Please take note that we will not be answering the questions through voice chat, and that leave your questions in the Q&A sections on the right-hand corner of your screen. And we will have a Q&A session at the end of the presentation for any of the questions that you left there. Okay, so our first presenter will be Sandeep. Sandeep, you can go ahead.
Yeah. Okay. Thank you so much, Sam, for the introduction. I would also like to welcome everybody on this Intel oneAPI Base Toolkit, starting up with that. This is going to give you a real insight on how oneAPI can change the way you have been doing and working around. I'll give you a brief introduction about NetWeb first. So we are actually present in about 5 countries. We have got thousands of customers, and we have got about more than 500 HPC installations all across. We have been delving with accelerated technology, and we have been doing a lot of GPU and other installations. We have been doing cloud implementation, many of them, and also across 5 countries, basically. We are into AI and big data, and we do serve in various capacities. Like, for example, you have got a project and you want us to do the AI related stuff for you, the data science related work, we can do that. If you have got a problem to route your data from various sources to a centralized big data and do the analytics there, we can very well do that also for you. We have been the largest server provider in this region, and today we do have 3 integration facilities around this region. So we are well versed with giving you complete solution with the design, development, pre-sales, and post-sales kind of a stuff. So coming down to a brief about our solutions, basically we do have solutions on data center computing. We do have about 500 or more servers on our website. You can go and choose among themselves. And if you are not feeling comfortable there, or you do still need something extra, do come to us and we can still customize the server for you. And it can be as good as for the workstations and other technologies. Talking about the storage, we do have a unified storage solution, which is basically NAS, SAN, and VTL in one box. And it can connect to any kind of a network, starting from gigabit Ethernet, 10G, 25G, 40G, InfiniBand, OmniPath, and you talk about any of those kind of a network. We do also do a lot of implementation on SAF and Cinder-based, cloud-based storage solution. We do have a specialized surveillance and archival storage solution. Our surveillance storage solution is also certified with likes of Milestone, which are the industry leader in the VMS side. We also have got a storage solutions specifically designed for InfiniBand, as well as we do have parallel file system storage solutions with us. On the HPC side, we have got a whole gamut of this. We do also have our own management tools where you can do a very easy and fast deployment. We do have our all kind of a templates which are there, and you can do your management of your cluster very easily with our tool called TCM, basically. And you can just talk about the application. Most of those applications are there already, and you can quickly deploy, redeploy, and things like that. On the cloud side, we pretty much work on all these things, public, private, and hybrid cloud. We do also have the cloud tool. We have got a cloud suite also with us, and we are also delving into hyper-converged and other stuff. Today, on the hyper-converged, we are also going to launch a product which is going to be called as Skyless. On the big data, as I already mentioned to you, we do have a whole lot of things which we can give. And coming down to the containers, we do have 2 platforms. One is Tyrone Container Platform, and another one is our platform called Kubites, which I would be definitely delving in deep depth once I go ahead with my presentation. So some of our engineered solutions, as I mentioned to you, Tyrone Container Platform, basically a Kubernetes upstream Kubernetes based platform, which can help you out in managing your Kubernetes based cluster. And we are designing a lot of products, in fact, appliances also based on this particular platform. Tyrone Kubites, I would be definitely speaking in detail, and this is one of the platform which is going to be really very, very useful for people like you. Coming down to Skylers, we do have a hyperconverged storage, basically in a box, and this is going to be very easy cloud in a box kind of a solution, which can grow heterogeneously, including solutions like GPU and any other stuff you can put in into this. It is going to be very, very easy to use and to deploy. And for other things, we do have a hyperconverged cloud solution, which is a cloud package of ours. And these are completely engineered solutions from NetWeb, which comes to you. We do have an innovation research and development team, which keeps on doing the development and on the new products and solutions, which we deliver to you. What today we have got all these products which you see and which we are talking about has been referred by our customers. They have talked about their pain points, and that those pain points have resulted in these kind of products and solutions which we have designed for you. On the services side, we do a lot of services like HPC planning, consultancy services, also taking it to the cloud and things like that. We do have the AI labs with us, backup disaster recovery related stuff, any migration related stuff, data center services, and other stuff which we can do. On the AI labs, as I was mentioning to you, we do have a complete, we manage the complete life cycle of an idea or a project which you might have in your mind, right from data acquisition to modeling, deployment, testing and training, and doing all a whole lot of things, including deep learning, machine learning, and whatever. So if any of our customers have any of those requirements and they need our help, we do have a whole gamut of data scientists, analytics, and also the big data engineers who can design entire hardware, software, and all those components for you. So as I was mentioning to you, we have got about 5 locations, and in countries like India, we do have about 12 regions. We do have 3 production sites, sorry, and about more than 250 employees actually. So if you see, this is our basically our customer base. You can see that we are into most of the areas. Talk about industries like maybe education, R&D, large enterprises, and ITES, a whole lot of oil and gas, media entertainment. Right. So let me talk about once we go to oneAPI. Before that, let me talk about some bit of things on what is happening on the multi-accelerator side. Today, one accelerator is not enough. We need more computational power and also cost efficiency today. And then we do need a cloud and a edge computing, basically. We need to have a different strategy for both of them. Faster insight is a no-brainer. Everybody needs a very, very fast insight, and this is a game which is being played, and we still need more faster insights. And multi-accelerator architecture is what is going to be the key as the industry moves forward. So why a multi-accelerator strategy for AI? We have to see that there are various things which various components are there, like learning, inferences, edge. So we need to look into all these levels and what kind of computing is required, what kind of a price, and what kind of a solution we can build up in these kind of segments. So what we have been seeing that the learning market has been growing. A lot of learning is happening. But what happens to this learning? This goes to for inferencing, right? So once it goes for inferencing, the inferencing market, the learning market is leading the inferencing market, and inferencing market is definitely going to be much bigger and larger than what a learning market would be. And with the time, this is going to go much more higher. And another thing is that, the learning hardwares are typically quite expensive, right? And if they are expensive, we cannot use it for inferencing. We need to have a separate hardware for inferencing where we require the bulk, and it cannot be the same hardware for every solution. We also require a programmable hardware and parallel processing today, and we need to see that how we can make this as a part of our strategy when we apply this AI to our customers. Most important thing is, today we do have a fixed dollar or fixed money budget, basically, and also maybe fixed power budget. So these are very, very important, and the design, whatever solutions we design, has to basically fit these two things to make a AI project viable. And for that, a multi-accelerator architecture would be imperative. We have to definitely look into that. So getting into another part of this is, suppose a edge device cannot have a same horsepower or a same kind of a performance which is there in learning or inferencing. So we need to see that what kind of a edge we can do, what kind of softwares need to run at the edge, how we are going to deploy things. These are all going to be very, very important when we put up our strategy towards addressing AI needs. Just to give you an idea that how on the data center and on the edge, how the inferencing and the training market are looking like, and how the growth is, you can clearly see that the inferencing market is still large, and it is going to grow much more higher than what it is right now. So definitely, I would like to say that, inferencing is one area where we need to have a proper strategy and see that how we can deploy better. Talking about few of the AI ecosystem and those kind of things. So we do have this various accelerators like GPU. Also, CPUs are becoming very powerful, FPGAs and edge computing. We do have the middlewares like containers and VMs, which are required for a very fast deployment, because there is no one tool and there's no one application you need. You might need a lot of applications like Cafe, Theano, TensorFlow, and things like that. And we have got programming paradigms like oneAPI, which is actually trying to help us out so that we can work across this multi-accelerator technology, and also Kubites, our Tyrone Kubites, TCM, and container platform, helping you out in trying to see that you try to achieve what oneAPI is trying to give it to you. So this is the entire ecosystem on all the three fronts where the things are going and growing. Talking about Kubites, so Kubite is a curated catalog for accelerated containers, basically, and they are all optimized for different applications. It is not only HPC or AI; it is both, and we are going to add more containers on this. Currently, we have got 50 plus applications and 100 plus containers which are there already, and we are adding up things much more faster. We do have Qubite certified things. I will be talking about those. Uh, Coming down to some of the applications, these are some of the applications which are already there in Qubites. So basically three things, it's a three-step process. So you get access to the Qubite cloud. You can run your applications. It can be a GPU, CPU, FPGA, or any kind of this kind of architecture. It can support all of these, and you can deploy various applications, in matter of seconds. You need not worry about the deployment time, whether checking up whether it is correct or not, and hand holding and things like that. It is just very, very fast to do that. So as I said, it is a repository of containers, works for GPU, CPU, and FPGAs. It is a innovation in second. Whatever you want to do, you can just go pick up the container, run your code, and just get the result out. It is a very simple design, and we do have workstations and clusters which can work equally with Qubites, basically. So you can run, another advantage is you can run multiple applications in a same workstation with various containers into one workstation, or in your cluster and your servers. It is a very simple deployment, and today we have got gigabyte certified systems which are available on Tyrone workstations, as well as Supermicro workstations. It is already certified hardware is already available with us, and it can be readily used using them. uh, it is absolutely reducing your IT cost and your development time and people time, and time is money here. And it all comes with a AI expert, a Tyrone AI expert, and our advices and our handholding to your team. So this is how typically it will work. You can pull the container within seconds, and you get a huge amount of bare metal kind of a performance out of that containers, basically. Yeah. So that is all from my side. I will now like to invite Subarna from Intel, who is a technical consultative engineer with Intel, to give us the insight on one API tool and to get us started with that. Right. I'll just close my sharing. Over to you, Subarna.
Yeah, thanks, Sandeep. Let me share my screen. Just a quick check. I hope my screen is visible and my voice is audible. Hello.
Hello?
I hope my voice is audible and my screen is visible.
I
Yes,
can
yes, Suparna.
I can see, yeah, yeah.
Yeah, thanks. So hi, good morning, and welcome all of you to the oneAPI workshop. So here, our main focus will be on data parallel C++. I'll start with a brief introduction of oneAPI, and followed by introduction of data parallel C++. Then I will take you across through the bits and steps of how you can write data parallel C++ programming program, and then I'll give you a demo of how to compile and run a data parallel C++ program. Then we will have a short demo about the compatibility tool, and I'll also introduce you to what is a data parallel C++ compatibility tool. So with that, let's get started. So as Sandeep was mentioning, in today's world, the application workloads are different kinds, are various, and there are so many kinds of hardware to deal with separate, like individual workloads. So each of these workloads and hardware, for each of these workloads and hardware, we need to maintain separate language libraries and middleware. So the cost for maintaining cost of maintenance for these individual systems are huge. So to deal with that, Intel has come up with one API solution. It basically works across different kinds of workloads, as you can see, scalar, vector, matrix, and spatial. It works across different hardware, CPU, GPU, FPGA, and other accelerator. And the solution is one. So you can have a single language or a single set of tools that you can use across all these workloads as well as different kinds of hardware. So with that introduction of oneAPI, let us now move on to what is data parallel C++. So data parallel C++ is the language that has been introduced as a part of Intel oneAPI. So the data parallel C++ is based on C++ 17. So it takes the goodness of the C++ 17 version, and it also has certain features of C++ 20 as well within it. With that, it also incorporates the SQL space. So it takes the goodness of the SQL language, which basically helps the program to run in heterogeneous platforms. It also goes ahead and incorporates its own features which are there as a part of SQL Next, and all this together comprises of the data parallel C++ language. Some of the features of this language are like it is a very high level language, and it can run across various architectures like CPU, GPU, and other accelerated devices as I was mentioning earlier. And the goodness of this is the same code you can reuse to run in all these platforms. Like the same code can run across CPU and other accelerated devices. You don't need to modify anything for that. Again, it is a open source implementation, and we take customer feedback to improve our language every day. And any features and or extensions that a customer wishes to have as a part of this language are readily accepted, and we can implement that as well. So these are a few goodness of our data parallel C++ language. With that in mind, I'll start going through a program. But before that, I think most of you who are acquainted with C++ will be acquainted with what are lambda expressions. So I want to just give an overview of that in case you are not acquainted with, so that uh, when I go across the program, because our kernel basically uses lambda expression, it will be easy for you people to understand. So basically, what are lambda expressions? So as you must be aware, most of you must be aware. So lambda expression is something where it is an anonymous way of declaring a function where like the function is defined in the same place where it's declared. The function, like you can see here, the function here is passed as an argument in like this lambda function is passed as an argument in this sort function, and it has been like implemented in the same place where it's defined. So it can be passed as a part of any function, or it can be defined, or it can be implemented in the same place where basically it should have the definition. So, and it's also anonymous. As you can see, it doesn't have a name associated with it. So some features of the lambda expressions are it should have a capture clause. This is known as a capture clause. What this is used basically is, suppose inside the function you want some values which are used outside this lambda expression to be used inside this function. So you can pass those here. Suppose if you want to use the x which is defined here, you can pass x as an argument here. Again, there are two ways in which you can pass this variable. You can pass it as pass by reference, or you can pass it by its value. So if you want to pass it by reference, you need to mention ampersand x, and if you want to pass it by value, then x is fine. And then followed by what all variables or the parameters you want to use inside this lambda expression. And this entire thing consists of the body of the lambda. So as you can see, the entire thing is this entire function is implemented here, and it returns the absolute value, and this absolute value is passed as an argument in this function. So it is an anonymous way of defining the function, like it of implementing the function in the same place where it's invoked, or where it's defined. So going ahead, let us concentrate on how the program is executed. So in heterogeneous programming environment, we will have a host, and we have one or multiple devices which are associated with that host, where we usually offload the kernel, which needs faster execution. So in our host, we have buffers and accessors. What buffers are is buffer is is a part like buffer reserves a part of the memory from the host which can be used in the device. So basically, if you can think of it as a data type which is used for passing a certain amount of data from host to the memory. Accessor gives permissions of like how to access that buffer. So it can be a read permission, a read write permission, or a read write permission, and several other permissions are there which you can give to a buffer. It's basically how you want to access the data that is already there in the buffer that is decided by an accessor. So the next step is the host queries whether a device is available or not. So because before offloading, it wants to make sure the device is available. After that, the buffer is passed through a command group handler, which finally offloads this uh, this data, whatever needs to be, or the kernel, whatever needs to be offloaded in the device to the device. So, what is command group handler? Is command group handler is basically you can think of it as an encapsulation. So, the buffer and the accessor is encapsulated in the command group handler, and then it's passed through the queue to the queue which basically offloads the buffer to the device. Uh, Actually, these are all theoretical expressions. In the next steps, we will actually go through a program where you'll understand these concepts better and more clear. So we will go across a vector add program, but since it's a heterogeneous world, so it's known as the hello world program of the heterogeneous world. So in the first step, we need to include the headers and namespace. CLSQL.hpp is the header we need to include in all of our programs in BPC++. And also the namespace CLSQL is a namespace which we need to include for all the programs. So one thing to keep in mind here is if you want to include other headers that are required for executing your C++ program, they're mostly same as C++17. So you need to include all of them after the SQL HPP header and not before that. So CL SQL HPP should be the first header of your program. In the next step, as I mentioned, we will create buffers. Since we are doing a vector add, I have created three buffers here. Buffer A, buffer B, and buffer C. So what after the buffer keyword, we have given the name of the buffer, and what parameters we pass is suppose we have an array A declared, so we are passing the entire array A. The range is size. A is of size. A size ID. This you can give a arbitrary size here. I have just taken the random size just for the ease of understanding. Again, we have passed the entire buffer. The entire size is passed. So we have a range parameters which actually defines how much of a array you want to pass in the buffer. So we can see all these three arrays have been passed. The entire arrays have been passed in the buffer. So the size of the buffer is same as the size of the array. As I already mentioned here, so we create buffers to reserve memory on the device and host in the device and host and initialize the memories with the host values. So we are initializing these buffers with host values. This A, B, and C are the array values that are there present in the host. Okay, in next step is we create a command queue for specific selector. So each each device should have a specific queue. So how that is decided is we are defining here a GPU selector. So GPU select we are creating an object of GPU selector, and we are now creating a queue object where we are passing the object of this GPU selector. So now here the queue will be created that will basically point to a GPU. Similarly, we can have a CPU queue and there is an Intel extension of an FPGA selector as well. So we can have a queue that's specific for an FPGA device. And And one more thing to note here is you can just mention queue my queue instead of defining what kind of queue you want this queue to be. In that case, it has its priority, and like the device which has the highest priority in your system, the queue will be created for that device. But it's always a good practice to mention the device when you are creating the queue, because you will be sure like where you want to offload your kernel into. So in the next step, what we do, we will submit the we want to submit the kernel in the queue. For there, what we need is, as you can see here, this is a Lambda function, and it has the same syntax that I explained to you before. Just for the ease of understanding, I explained to you before I came to this step. So it has a capture clause, and it's passing all the values by reference here. And this is what is known as a command group. So what command group does is, you will also see in the next step, it actually encapsulates the entire kernel and passes it to the queue. So queue dot submit, whatever is passed inside that is the command group. It also has a handler, and that is the only argument that's uh, passed through it. So these are the few accesses that are passed in. These are the accesses that we pass in the program. So here you can see that we have passed three accesses, A, B, and C. This defines how we want to access the buffers, as I already mentioned. Here I want to access A buffer in a read-only mode, and B buffer also in a read-only mode, and C buffer in read write mode. Because it's read write, we don't need to specify anything for this. So basically what we will do is we will read the content of A buffer and the content of the B buffer, and after adding those two content, we will store the result in a C buffer. Okay, so this is the next step. This is the actual kernel that we are offloading in the device. So here we can see we have defined an iterator that will iterate across these three buffers, and the and each of the element, like each element of A and each element of B, will be added individually, and the result will be stored in this individual element of C. So here we can see this class vector add. This is the name of the kernel that we have given. This is optional, like you can skip this step of adding a name to the kernel, but it's a good practice to give a name to the kernel. Also, you can see I have mentioned parallel for here, so that this addition takes place parallelly. So if you want any part of the code to execute like in a serial manner, you can mention single task as well. So in if you mention cgh dot single task, then your kernel will be executed in a serial manner. Here you see I have mentioned it in parallel for, so that our execution is fast and it executes parallelly. So these were the bits and pieces of our code. Here is the entire code. So just for a quick recap, you can see like initially we have this three arrays, and then we created buffer. We passed this entire array in the buffer. Then we have created a queue. We have submitted a command group in the queue that is having accesses also, that gives us an idea of how we can access the data in the buffer. And then finally what we have done is we have passed, like we have declared the kernel, and we have instructed each to execute in a parallel for manner for quicker execution. So this was most of the code, and finally what we have done is we have displayed the results in the host side of the code. So if you have, so this entire portion is the host, and the small portion, as I mentioned, is the kernel. But one thing, if you have noticed, is that when uh, when uh, when I have printed this, I have not copied the data back. So initially, as you can see, I had copied the data from the array to the buffer. But here, after the execution have ended, I have not copied the contents of C from the buffer back to the array. But when I am printing the array, I'll get the correct result. So this is one of the like beauty of data parallel C++. So the beauty is, if you mention this and the entire program in this scope, the scope operators. So after the scope is finished, then the buffers are destroyed and the entire content of the destructors are called, and the entire content of the buffer is copied back to the array. That is how you get the C values even in the C array, and when you print, you don't need to explicitly copy it back. Okay, the next question all of you will have is from where you, if you want to test this, from where you need to download. For that reason, I have included the URL, so you can directly go and download one. Like you can use data parallel C++ compiler from oneAPI Base Kit. So the URL is given here. Please use this and let us know your feedback. With this, we will move to the demo of whatever program we saw, and you'll get an idea of how we actually compile and run the program. Okay, this is a program that I was showing you. So uh, I have initialized the values of the array, and otherwise the exact same program is there wherever I was showing you. So the first step is you need to source. So I have oneAPI Base Kit installed in the system. First step is I need to source the compiler for compiling. So this is done with this. So this is sourcing not only a compiler, but it's a single step that's sourcing all the tools. If you want to just source the compiler, go ahead and choose compilers, and within env you can. I'll show you. Like if you just want to source a compiler, you need to go to oneAPI, then compilers, then env, and vars.sh. So if you are sourcing this, it will only source the compiler. But here I have done sedvars.sh that will source all the tools for me. The next step will be a simple step, that is you need to mention dpcpp, that is the name of the compiler, then the file that you want to compile, that is vectorad.cpp here, and then you can mention a object name. That's it. Your code is compiled, and we can run the code now, and we can see this is the values of C after addition. So as you can see, it's a very simple procedure to compile and run the program, and write a DP++ program. One more thing I want to mention in this part is that usually the people, those of you who will be acquainted with heterogeneous programming will know that usually in heterogeneous programming we have separate files for the kernels, like whatever we want to execute in the device, and whatever we want to execute in the host is also in separate file. But in DPCPP, that is not required. A single file, as you saw there, can have the code for both the host side as well as the device side, and it executes like a magic. And so the lines of codes are also reduced here. So the ease of use is maximum in this program. As I mentioned, DPC++ is open source, and we have a few samples. There are actually there are samples from all the specs of different workloads and like different architectures. So all of you are requested to go through these samples and try them out so that you get a feel of how to use this tool and get used to it. Just to summarize, DPC++, it is a programming language specifically for a heterogeneous platform, and it has open standards. And the standards committee work together for making this language even better day by day. We take all your feedback because it's open source, and your feedbacks are like encouraged. Go ahead and open this URL and provide your feedback. And another thing is it's very easy to write data parallel C++ program because mainly because it's a single source program, and the steps if you compare a OpenCL program with a data parallel C++ program, you will see in real time like almost it's almost like less than half of the lines of code if you compare. So it's very easy to write. So go ahead and try your first data parallel C++ program. Provide us feedback in this URL, and let us know how we can improve the language and make it even better. With that, I'll introduce you to a like very unique and special tool that Intel has come up with. This is known as Intel Data Parallel C++ Compatibility Tool. It's an Intel proprietary tool. So what it does is for people who are using CUDA code and they just want they want to try our DPCPP code. What we have done is we have introduced a tool that will migrate most parts of your CUDA code to data parallel C++ code. So it's a very easy steps. What we need to do is we just need to run a few steps that will migrate your project in CUDA to DPC++ language. But it only ensures that on an average it will migrate 80 to 90% of the CUDA code, because for some portions there may not be one-to-one mapping. And so in those areas where this tool is not able to migrate the code, the user or the developer manually needs to go there. You will get all the warnings of the portions of the code that have not been migrated and why those have not been migrated and what you can do for that. I'll show those things to you in a demo. So what you need to do is you need to go to those lines that have been mentioned in the warning. Follow the tips of how you can modify it, and then just edit those lines of the code, and your code will be perfect to run in a DPC++ compiler. So the documentation of the compatibility tool is there. Compatibility tool is also present as a part of BaseKit. So when you are installing BaseKit, you will install the compatibility tool as well. So with that, I'll give you a small demo of the compatibility tool. So this is a vector add code in CUDA. This is a vector add code in CUDA. What we will do is we will migrate this code to data parallel C++. So first step is sourcing. So you either use adverse, or similarly you can go inside the compatibility tool in opt Intel and source the vars.sh only for the compatibility tool. And the first step of this is we will we will run this command dpct, and then we will give the input root, like it will point out to where is the file that you want to migrate. Since it is there in the same folder from where I am running this, I have given a dot here. Otherwise, you need to mention the full path. And then I have mentioned the output root. This is usually the folder where you want the output to be present. I want it to be in the dpct output folder, that will be there in the same folder where I am running the code. So I have just mentioned dpct output here. So when I am migrating the code, I see there is a warning here that mentions that the migrated API does not return error code. So why this comes is the CUDA language uses error codes for pointing out errors, whereas DPCT uses doesn't use error code like this. So what it has done is, if you see here, it has created the DPCT output folder, and within this we have this migrated file. This is almost migrated, except for the fact that only like a few lines have not been migrated. Let me scroll down. Yeah. So it mentions that this has been changed and the error code has been removed so that it always points to 0. But that is why its status is redundant here. So if you see the CUDA code, the status was there. The status here was like determining whether it's a success or failure. But since it doesn't return a code in the DPC++ language, so I would suggest you remove the status variable itself here, because I think it's not required here. So it has been written that you may need to rewrite the code. How we can rewrite the code is, since we don't need error code and this entire code, like the entire code has been put in try-catch block, which is the approach of DPC++ language. What we can do is I'll remove the status variable itself. So what I have done is I'm commenting status from here, commenting status from here also, and I am just keeping this portion of the code down. Only this one line of change I am doing, and then following the same method as I mentioned to you before, I am compiling the migrated code, and it migrates perfect for me, and I get all the outputs here. So yeah, that was a short demo of DPCT tool, why it's used and how it's executed. And so the like DPCPP session is like a day long session, and like there are so many ways I can deep dive into the language. But as an introduction, I think whatever was shown to you was the starting point. If you start to explore, you will find like you will find new interest and new questions. So go ahead and ask us those questions, and we are here to resolve those for you. With that, I think I am done with my portions. I think it's fine if we take questions now. Thanks all of you. I'll stop sharing.
The from DPC++ to CUDA on whether compatibility tool can be used for converting DPC++ to CUDA.
Okay, yeah. So compatibility tool is a one-way tool. It cannot be used to migrate the code from DPC++ to CUDA, but other competitors are coming up with tools that can make that possible. So yeah, search the internet for that. So we have other we have other competitors who are working on that. But yeah, CT is a one-way tool.
Yeah. So just to clarify the intent of this tool, because there are a lot of course, CUDA code that is existing. We want to make users' life easier by just providing this simple tool that can migrate the code from CUDA to DPC++. Right. So that is the whole idea of this tool. And so Subhanathan, I think the next question is around. I hope I hope it is clear. Subarna, the next question is around, can there be a single queue to offload the kernel into multiple devices?
No, actually, the queues are specific for a particular device. So when you are creating a queue for a particular device, it's only for that device. So each queue should each device should have its own unique queue. So yeah, the answer is no.
And can we use pointers instead of buffers to write DPC++? I hope you meant DPC++ code
Yeah,
branches. Yeah,
yeah.
go ahead.
So DPC++ code can Yeah, DPC++ code can also be written in a pointer-based approach. Since there was short of time, I didn't go in details of that. So that kind of code is known as USM or Unified Shared Memory. That is another way of writing DPC++ code where you can use pointers. What you do is again there are two ways in which you can write a USM code. So you can just you can just copy the pointers from device from the host to a device using memcopy, or you can use a shared like there is a specific memcopy for that, or you can use a shared malloc command to reuse the pointers use the memory that has been allocated by the pointer in the host to write a program. So in one word, yes, it is allowed. And the links I have provided you for the open GitHub open source, please go through that link and you will have a clear understanding on that. And also I'll share my slides with all of you, and in the backup slides you will get USM concepts clearly, and if you have any questions, we are always there to answer.
Right. Any other questions? I've got few questions on qubits. I will keep on answering, and if I get any other questions, we can still take them. On
There is
qubit,
one question, I think, Sandeep
yeah, please.
ji, this is how it handle the kublas calls in code. Does it automatically point to MKL? I think Subarna,
Yeah, Suvarna.
yeah,
Yeah,
Rubna or
yeah,
Milind, do you
yeah,
want
yeah.
to?
Let me answer this. So, yeah, sure, Ritesh. Thanks. So, most of the CUDA libraries functions like the kublas has an equivalent MKL, and in most cases, it is migrated to the MKL equivalent call. But I'll not tell it's 100% migration. Like for some functions, there may be an equivalent MKL, and that may not be migrated. But the cases are rare. And if you have such demands of a function that needs an equivalent MKL, and that's not present as a part of DPCT, please go ahead and raise the concern to us. We'll make sure that is also implemented. Yeah, thanks.
Right. Okay, still people can put in the questions, and Subarna is there with us to answer. Meanwhile, I'll try to answer a few of the questions on qubits. Uh, is qubit already launched? Where I can find more details about it? So yes, qubit is there right now, and it is available. And you to find the details, you do have the details of the people out there on the Q&A session slide, which is on your screen. You can get in touch with them and they can help you out with more details on that. Want to know about the qubit costing? Same, I would say that please do get in touch with our people, and we will be helping you out with those costing and other stuff, how to go about it. Uh, is qubit supported in any of the system servers you carry? Later, it is possible to make available listing of certified models. So yes, we do have supported systems which supports qubits, and it is possible to make the certified list models also. We do have from right now from Tyrone and Supermicro models, which are basically qubit certified, and they can be used for using qubits. And if I have a request to get a customized containers, can you do the same also? What can we use qubits on a cluster? So yes, honestly speaking, yes, you can get the containers. This is what we are trying to help out with our customers also. So if you have got any unique requirement for customizing your containers, do come to us. We will definitely try to help you out and try to put in your containers and make it ready for you on qubits. And qubits can be used on cluster, and we are planning one more cluster kind of a thing called qubit appliance, which might have a Kubernetes engine to do those kind of cluster management on qubits, right? So, do we have any more questions? Okay, so yeah, so I don't think we do have many more questions now.
Okay.
Yeah.
Okay. So I'll just wrap this up. Okay. Just help us to fill up the feedback form. Okay. So I put up a banner above. Just click on the link, and then you'll be able to go to the feedback form, and you can help us to fill that up so we can get some feedback in terms of if the webinar is effective or not, if the content is effective or not. And also, yeah, like we said before, if you have any further questions, you can write to us at info@netwebtech.com, or if you want to go to specific regions, the information is written on the Q&A session, the slide as shown. We are having the third series of the Tyrone-Intel oneAPI webinar that it will be coming soon on the 22nd. We will be putting all the details on our social media pages, and we will also be emailing. So just look out for that. And also, if you want the resources for any of the webinar in terms of recording or the presentation slides, we will be compiling it into our Tyrone blog, and then we'll be posting on social media. So you also can look out for that on the social media pages. So this, I'll just leave the session open a bit longer so that anybody that can help us fill up the feedback form can do so now.
Also, like since we have some time, if there is some request for the USM display, like I can show the USM code also, but let's wait for the questions. Like if people have more questions on USM, I can just display the code and make them understand how it is done, like the pointer best approach, whatever we got a question.
Yeah, maybe.
Yeah, we can do that. I will stop sharing and you can proceed with that.
Okay, so I'll just show you the two different ways of how we can write a code in USM. So as I mentioned, there are two ways. One is the implicit way, where you actually copy the data from the host to device using a mem copy, and one more is where you use a malloc shared to reuse the same memory that is allocated on the host. So we will go across the implicit way, that is the malloc shared way, and then we can go across the next approach. So here we see we have data in these two pointers, like data 1 and data 2, and we are allocating shared memory. That memory can be shared across the host and devices. So we have created a queue. So we have not mentioned which device selector. So by default, it will create a queue that with like for a device that has the highest priority in your system. And then I have allocated shared memory, and then I have initialized this to two data pointers. And then similarly, like the buffer approach, I have written my kernel in the exact same way. And so this here we don't have the scope resolution operator that will copy back the code for us. So it's a good practice to copy back the code, and we are waiting for the kernel to get completed here, and then the copy back happens, and we are like outputting here. And finally, we should make sure that the data is freed after the code is written. So this is a first pointer based approach of writing the code. And next, this is the explicit way in which we are allocating memory in the host. And then after that, we are allocating memory in the device. So you can see A and B are the host pointers, and DA and DB are the device pointers that are equivalent to this pointers here. After that, what we are doing is we are using explicit mem copy to copy the device, copy the data from A to DA. And after that, after we have copied this, we are creating we are creating the dependency tree ourselves. Like we have mentioned here that E1 depends on E2, so that we make sure that the first one executes first and the next one executes after that. And after that, similarly, I have mentioned the kernel where we are doing the addition, and then we are copying back the data from the device to the host, and at the last we are printing. Finally, we are freeing the data. So yeah, this is the explicit way of writing a USM code. So people who are very interested in like the pointer based approach of DPC++, here you go. Yeah, I think yeah, that was a short like demo of how to write a code in USM. Yeah, I think thanks. That's it.
Thank you everybody for attending the webinar.
Guys, for joining, and thank you, Subarna, for this excellent presentation.